What I'm going to do now is go back to the quiz that everybody finally did take the quiz. And it's worth looking at. All right. This is that chemistry review quiz. This up here is a distribution of people's scores. This is like, if you take a look, and this is actually one, two, like a third of the people in the class or so got like 50%. You know, the number of people that actually got 90% and above was like 3 out of the entire class, which at this point is not a problem in terms of, you know, none of this is, the first test isn't for another month or so, but like any of the questions on this quiz could end up like on your first exam, or the quiz for that matter, because these are all very important concepts that we're going to be building on for the whole semester. So I would say if you found yourself down here or kind of confused about things, please do not wait to kind of start catching up on that, or don't assume like, I'll pick it up as we go. Because I think what will happen is you'll just get more and more lost. So this is, you know, what do we call it? Proactive. I like that word. If you are more passive in this class and just kind of hope it's all going to work out, that's how people kind of just slip through the floorboards and drown in the class. So please, please don't. And it can be tricky in the beginning because I know people get discouraged. They like see this stuff and it's like, oh crap, I'm not going to be able to, I'm so confused. It's not uncommon. It just means you need to like kind of breathe and like do whatever you do to like kind of stabilize yourself and just kind of, what is it, like that old Christmas thing, 1 foot in front of the other, and soon you'll be walking out the chemistry door, whatever. So yeah, I can say just personally, I've in like the data analysis I've been doing for the fMRI work, there's times when I'm like, oh crap, it's just like looks like the, you know, the stuff I need to learn to do the next stage of the analysis is just, it's depressing sometimes even. And but then it's just like, all right, let's just dig in, and eventually you get through it. I guess I'm saying that just because I'm assuming a lot of people are, you know, do have a bit of work to get up to speed in the chemistry based on this. All right, so let's take a look at each of these because it is worth. You know, in a glucose solution, which type of chemical bond is responsible for the attraction of the water molecules and the glucose molecules? Again, here, you know, 70% of the people did get the hydrogen bonds. That's what we've been talking about. Those are those kind of more temporary electrostatic attractions between the local charge imbalances. You know, ionic bonds, definitely not. Covalent bonds, not either. Covalent bonds are much stronger, and those are the things that would, you know, share electrons more intimately to make an individual water molecule or an individual glucose molecule. Which type of bond is responsible for the attraction between the individual atoms that make up a single glucose molecule? Again, here we're around 75%. Again, it's those covalent bonds, that intimate sharing of electrons. And again, that single glucose molecule stays intact as an entity, even when you dissolve it. Even if individual glucose molecules are no longer in their larger crystal, each individual, you know, C6H12O6 stays intact as a covalently bonded entity. Well, what type of bond is responsible for the attraction of the individual atoms that make up the molecule of NaCl? So most people got this. Ionic bonds. This one, only 24% people got it right. What type of bond is responsible for the attraction between the individual atoms that make up a single water molecule? So at this point, are there any questions why the right answer here would be covalent bonds? Right, because the individual water molecule is two H's and an O connected with that intimate sharing of electrons. Between two separate water molecules, we have hydrogen bonds that are attracting them together. But between the three atoms that make up one water molecule, it's covalent bonds. If you change the number of electrons of an atom had, it would now be an ion. This should not be 60%. Hopefully after today, this will be 100%. If you add or subtract electrons from an atom, you become an ion, a charged atom. Isotopes are if you change the number of neutrons. Definitely not. Yeah. What would we have to do to make it a different element?
Change the number of protons.
Exactly. We change the number of protons. Which of the following solutions would best conduct electricity? Again, 75% of the people got salt water, which just from your intuition, like, hopefully. This one, oh my God. So over a third of the people did not get this. 1 mole of any element has the same blank as a mole of any other element. This will be important. This is going to be the main way that we denote our concentrations, is molarity or osmolarity. And like, I'm not forgetting who said it, but somebody a little bit ago was saying, it's the same number of atoms. That's Avogadro's number, 6.022 times 10 to the 23rd atoms or molecules of any particular substance. And I'll talk about this in a little more detail as well. The mass or weight of, in fact, here we have over half the people said the same mass. If I have a mole of an element and I want to know how much it weighs or what its mass is, how do I figure that out?
You have to convert, right? You have to convert.
And how do I do that? Where do I find the conversion? Anybody?
You add up the atomic weight of each atom, and you basically, if you're talking about a mole, then instead of it weighing this tiny amount, a Dalton, it weighs a gram, right? So if you're looking at a whole molecule, you just add up the molecular weights of all the atoms that make up that molecule.
Yeah, and where do we find those molecular weights?
We can look at the bottom of its little square in a periodic table.
Yeah, exactly. So in fact, I'm in Google's image search right now, trying to find a nice picture to show you all, just because, oh, come on. Oh, okay, hold on. I'm looking for a nice one. Okay, this will work. Open a new window. Okay, I'm going to share this thing now, actually. I'm going to share. Here's a periodic table of elements. The vibrant periodic, because it's got all sorts of great colors. Sodium, Na, it has here at the very bottom 22 so you can just assume 23. That 23 is the conversion. 23 grams of sodium give you 1 mole of sodium. If I look over in chlorine, it says 35, basically 35.5 grams of chlorine gives you 1 mole of chlorine. So 1 mole of chlorine, has quite a bit more mass than 1 mole of sodium, way more mass than like 1 mole of hydrogen. 1 mole of hydrogen just weighs a gram. 1 mole of sodium weighs 23 grams. 1 mole of chlorine weighs 35.5 grams. And like we just heard, if you want to look at a compound, you just have to add up the atomic weights of each of the individual atoms that make up that molecule. For like sodium chloride, it's going to be 23 plus 35.5. So about like, 50, what is it? 58.5 grams of table salt gives you 1 mole of salt, or like 6 times 10 to the 23rd individual molecules of salt. So we're not going to do a lot of stoichiometry in the class, but you should know the basics of how to convert from moles to grams and grams to moles, because in reality, when you're actually making up real solutions in the real world, you can't count out moles. You weigh things out on a scale. So you need to know the relationship between the two. Actually, while we're here, just because it's interesting, I didn't mean bromine, I wanted chlorine. Okay, we can even say bromine. How come the atomic weight of this, given that we know a proton and a neutron are both 1 and electrons are negligible, how come a lot of these atomic masses are not integers? How come they are actually fractions like this?
Because they often occur as isotopes.
Yeah, exactly. There's different naturally occurring isotopes. So this is kind of the average weight. If you have a sample of this element, that's on average given the distribution of the naturally occurring isotopes. So that's why chlorine is 35.5 instead of 35 or 36, because about half the chlorines out there weigh 35, half of them weigh 36 because they have an extra neutron in their nucleus. They're both stable, they're both common. So but you should know the basics of mass versus molarity, or moles. Moles is number of atoms or molecules, specifically Avogadro's number if it's 1 mole. And then if you take 1 mole and you want to know how much, 1 mole is about the amount you can put in your hand. 1 mole of sodium chloride is a little pile of salt in your hand, right? 58.5 grams of salt. It's a little, so it's kind of a practical amount. Anyway, let's get back to where we were. Again, I'll talk about this a little more, and you're going to have it on a homework assignment and all sorts of stuff. If moles are not that clear to you, please go and brush up on what a mole is, because again, it's at the core of how we're going to be specifying concentrations for the whole semester. pH. I didn't talk about pH yet. What is pH even? What is it a measure of?
Measure of hydrogen.
It's a measure of hydrogen concentration. And basically, when the pH goes down, I'll talk about it a little later, but pH is kind of a weird equation. So actually, the more hydrogen that you have, the lower the pH number is. So when pH goes down, the acidity is actually going up. And the amount of hydrogen is actually going up. And alkalinity is kind of the opposite of acidity. So if pH is going down, alkalinity is actually less. Alkalinity is greater when the pH goes a higher number. But if I will talk more about pH in a little bit, or maybe on Tuesday. But pH is going to be critical for our class. pH is something we have all sorts of things to maintain homeostasis about, because if pH is off, it's going to denature proteins and it's going to mess up all your metabolic pathways. There's a pretty narrow range of pH that are compatible with life. You know, your body's around, what is it, around 7.4 or so. You know, if you go down below 7 or above 7.8, you're going to be dead. So we're going to talk about buffer systems. We're going to talk about the respiratory control of pH. We're going to talk about the urinary system, the kidneys dealing with pH homeostasis, all the different things that help control your pH balance so your system stays happy and healthy. Covalently bonded molecules will. So now that we've talked about it, why is this the right answer? Sometimes dissolve in water.
Depends if they're polar or non-polar.
Exactly. If they're polar, they'll dissolve. If they're non-polar, they won't. That's it. You know, if you change the number of protons, we talked about that, it would be a different element. And again, we talked about non-polar do not dissolve in water because of that like dissolves like thing. So any questions about any of these? So what I decided, because I really want to make sure everybody knows what's going on with these. So I just set it up so you can just take this quiz again. And I'm going to throw you into breakout rooms where you can talk to each other and make sure for each of these questions that you all converge on the same answer. And like in 15 minutes from now, I will hopefully see everybody with 100% on this quiz, because between going over this stuff in class, between going over it right now, between having a breakout room full of people that can all like check things, I want to see if we can actually converge on everybody getting the right answer to each of these questions. Because like I said, everything we do is going to build on these basic concepts. So if you're lost at this point, it just gets worse. It doesn't like get better. So I think it's set up so you can just go back in and take it again. And I am going to just throw you in the breakout rooms and we'll regroup like in like 15 minutes or so. So here we go. Boom.